On the morning of the 28th of January 1986, the coldest launch in the program's history sat on its pad, sheathed in ice. 73 seconds after it left the ground, all 7 people aboard were gone, the first in-flight deaths in American spaceflight. The fault that killed them was not exotic and it was not hidden. It was a ring of rubber about the size of a washer. And it took down a flight the whole country was watching. Aboard was Krista McAuliffe, a teacher chosen to be the first ordinary citizen in space. That morning, classrooms full of children watched the launch live. To understand how something so small undid a spacecraft, you have to understand the 2 white rockets strapped to its sides. Those solid rocket boosters were too long to ship in one piece, so they were built as stacked steel segments, and every place 2 segments met had to be sealed. Here is the seal up close. 2 rubber O-rings sat in the gap where the segments interlocked, a primary and a backup behind it. Now here is the part everyone missed. At ignition, the pressure spikes so hard that the joint itself flexes open. The metal walls bow apart by a fraction of an inch. The whole design depended on the rubber springing outward to chase that opening gap and stay pressed against the steel. The seal only works if the rubber moves faster than the metal does. Think of a rubber band. Warm, it snaps back instantly. Leave it in the cold and it goes stiff and slow. It lags. That lag is the entire disaster. The engineers knew this could happen because it already had. On earlier flights, hot gas had crept past the rings and scorched them. They called it erosion and blow-by. The worst damage had come after a cold launch a year earlier in January 1985. The colder the rubber, the more the fire got past it. And yet the recurring damage was not treated as a defect to be fixed. It was filed away as an acceptable, understood risk. Flight after flight, the danger became routine. One engineer would not let it lie. In a July 1985 memo, Roger Boisjoli of Morton Thiokol warned plainly that the joints could fail and that the result would be a catastrophe. Then, the night before launch, the weather turned. A record cold front was pushing toward the Florida coast. Overnight lows fell near 18 degrees Fahrenheit. By liftoff, the air would be around 36, roughly 15 degrees colder than any launch the program had ever flown. So, on the evening of the 27th, the engineers got on a teleconference with NASA and said it out loud: "Do not launch in this cold." Boisjoli and his colleague Arnold Thompson made the case directly. Below 53 degrees, the coldest they had ever flown, they could not promise the rings would seal. The recommendation was simple and physical. The rubber will be too stiff. We are outside what we know is safe. NASA's managers pushed back hard. Marshall's Lawrence Molloy strongly questioned the no-launch recommendation. Under that pressure, Morton Thiokol's senior managers asked to go offline. They caucused among themselves away from the engineers' data. In that caucus, one executive told the vice president of engineering, Robert Lund, to take off his engineering hat and put on his management hat. Led by Senior Vice President Gerald Mason, the managers reversed their own engineers. Joe Kilminster signed a go-ahead. The people closest to the hardware had been overruled. The launch was on. By morning, the right booster's aft joint sat at an estimated 28 to 31 degrees. The rubber there was as stiff as the engineers had feared. At ignition, the joint flexed open exactly as designed, but the cold, stiffened rubber could not spring out fast enough to follow it. For a critical instant, the gap was unsealed. Hot combustion gas blew straight past the seal. In the first few seconds, 9 puffs of dark smoke escaped the joint. The fire was already getting out. For a while, debris briefly plugged the gap and the leak sealed itself over. The shuttle climbed. From the ground, it looked like a normal ascent. Then the temporary plug broke loose. Around 58 seconds, a flame appeared at the breached joint, a blowtorch pointed at the spacecraft's own fuel tank. That flame raked across the external tank and across the strut, bolting the booster to it. Steel and tank skin began to give way under a torch they were never built to face. At 72 seconds, the lower strut failed. The booster, no longer held at its base, swung on its upper mount and pivoted into the tank. The tank ruptured. Liquid hydrogen and liquid oxygen poured out and ignited. At 73 seconds, the forces of flight tore the orbiter apart. It happened roughly 9 miles up at about 46,000 feet over the Atlantic. The crew cabin did not vaporize. It separated largely intact and fell for 2 minutes and 45 seconds. Investigators concluded at least some of the crew survived the breakup itself. 7 people were aboard: Commander Dick Scobie, pilot Michael Smith, mission specialists Judith Resnick, Ellison Onizuka, and Ronald McNair, payload specialist Gregory Jarvis, and Krista McAuliffe, the teacher, watched that morning by the classrooms full of children who had believed they were seeing something wonderful. When the Rogers Commission investigated, one of its members made the cause impossible to deny. The physicist Richard Feynman dropped a piece of the O-ring rubber into a glass of ice water. He pulled it out and it had lost its spring. In front of the cameras, he had reproduced the entire failure. The Commission's report, published that June, laid out the truth in 2 layers. The rubber failed because it was cold, but the launch happened because the warnings were overruled. There is a name for what went wrong in that room: normalization of deviance, when a danger keeps appearing without disaster and people slowly redefine it as normal. A known, unfixed flaw had been reclassified as routine, simply because it had not yet killed anyone. The data sat on one side of the scale, the schedule sat on the other. The schedule won. The real cause was not bad luck, and it was not really the rubber. It was a decision to fly outside the limits the engineers had drawn and to call a known, recurring flaw acceptable. The lesson is not that rubber gets stiff in the cold. It is that the people closest to the hardware said so and were not heard. Listen to them, and never call an unfixed danger normal just because it hasn't failed yet. The margin between routine and catastrophe can be as thin as a ring of cold rubber.